see that Salil is sharing his position this year among many institutions, but we'll hear about computational entropy.
All right. Thanks, Savi. Thanks, everyone, for coming. So I'll be talking about, mentioning in the talk things that are coming in a kind of line of work over the last few years involved with Iftach Heitner, Thomas Hollenstein, Omer Reingold, Ho-Tek Wee, and Colin Zheng. But most of the technical results that I'll focus on, the newer stuff, is from a new paper with my student, Colin Zheng. OK, so apologies, some of these early slides are from talk for a broader audience. I will kind of go through them quickly. So this work is about the foundations of complexity-based cryptography. Right, Shannon showed information theoretically secure cryptography in most standard settings is from most things we'd like to do is can't really be achieved. And so Diffie and Hellman suggested assuming the adversary has limited computational resources and basing cryptography on hard problems from complexity theory. And as we all know, the most basic kind of computational hardness that Diffie and Hellman suggested would be appropriate for cryptography is captured by the notion of a one-way function, a function that is easy to compute, it's polynomial time computable, but is hard to invert in the following kind of average case sense. So if you choose an input uniformly, say an n-bit input to the function, wrong button, uniformly at random, and you give f of x to a polynomial time adversary A, the probability that it can find any preimage should be going to 0 very quickly, specifically faster than any 1 over any polynomial in n. And I want to stress here that in the general definition of a one-way function, we don't require that the function is one-to-one. And that's why we insist on saying that it's hard to find any preimage of f of x. So this is a very natural definition. It seems one-way functions are, all right, so the first candidate example is multiplication. Multiplication is easy. The inversion problem is a version of integer factorization, which we believe to be hard. But one-way functions seem to be everywhere. It's almost hard to write down a somewhat complicated function without writing down a one-way function. But somewhat surprisingly, this notion that was suggested by Diffie and Hellman in that kind of founding paper suffices for a huge amount of cryptography. Okay, so through a series of works, mostly in the kind of mid-'80s and early '90s, it was shown that just from starting from any one-way function, you can solve many cryptographic problems of interest. So these results start out by building some kind of basic primitives like pseudorandom generators, things called universal one-way hash functions, which are a form of collision-resistant hash functions. And from these, you can build pseudorandom functions, solve essentially all the problems of private key cryptography, private key encryption, message authentication codes. You can even solve some seemingly public key type problems like digital signatures. You can construct zero-knowledge proofs. You can build secure protocols for secure multi-party computation, and solve it's remarkable how much cryptography you can do just assuming that there exists a one-way function. And so this work is about trying to understand this picture better and understand better how it is possible that we can do so much cryptography from one-way functions. We personally started on this project because of by kind of filling out one piece of this picture that kind of was one of the few pieces that wasn't solved by the early '90s, showing how to construct what are called statistically hiding commitment schemes from one-way functions. This was with Iftach Heitner, Min Nguyen, Shenjin Ang, and Omer Reingold. And in the process of trying to understand and simplify this construction that we had, kind of led us more to return to some of these more classic results and try and understand them better. Okay, and so the general project is to understand this bottom layer better, how we go from this basic assumption of one-way functions, or sometimes that my co-author Omer Reingold likes to refer to the raw hardness that we assume in a one-way function, and build these more these bricks, these building blocks that have more qualitative guarantees, right, that turn the raw hardness of a one-way function into these more qualitative guarantees, from which the kinds of constructions, there seems to be a real difference in the kinds of constructions you do at this level to the ones that you do at this level. From here up, it's reasoning in a much more qualitative way of composing these basic primitives to build solve more complicated problems. And there seems to be something different and yet common going on in the constructions down here, and that's what we're trying to understand better. Okay, so that's the goal, and this is where the title of the talk comes in, computational entropy. So the kind of answer that seems to be emerging is that every cryptographic primitive, particularly these ones at this first layer I was talking about, can be understood in terms of some form of computational entropy. And second, that one-way functions already have present in them a little bit of each of these types of computational entropy. Okay, and so doing crypto from one-way functions amounts to finding ways to manipulate these forms of computational entropy. Okay, and there have been a variety of notions of computational entropy studied in the literature, starting with the work of Yao. Then I'll talk in some depth about Hastad, Impagliazzo, Levin, and Luby, paper of Barak, Sheltiel, and Vigderson, doing a systematic study of various notions of computational entropy. But the starting point for us will be the notion studied by Hastad et al. Okay, but before getting to computational entropy, just a review of entropy. So in this talk, we'll really be talking a lot about Shannon entropy, which I assume everyone's familiar with. It's so we're talking about discrete random variable x. You take the expectation over a random sample of x of log of 1 over the probability mass. But actually, for the purpose of the talk, you just want to, if you're not familiar with entropy, just think of it as a measure of the amount of bits of randomness in the random variable x on average, right, because we're taking the average over random samples. And it is the entropy is sandwiched between 0, which happens if and only if the x is concentrated on a single point, and log of the size of the support, which happens if and only if the random variable is uniform on its support. And we'll also refer to conditional Shannon entropy. So we have two jointly distributed random variables, x and y. It's the average over y of the entropy of x conditioned on that sample of y. Okay, we will mention, so more often in talks in complexity and cryptography, one sees min entropy. We will mention min entropy from time to time. That's replacing the expectation with a minimum. And max entropy is just the upper bound on entropy that of log of the size of the support. And all logs are base 2 in the talk. So Shannon entropy is sandwiched between min entropy and max entropy. I like to think of these as kind of worst case measures of entropy, whereas Shannon entropy is measuring entropy on average. But Shannon entropy, when I don't specify otherwise, when I say entropy, I mean Shannon entropy in this talk. Okay, and so what is computational entropy? Notions of computational entropy arise from the fact that an algorithm with bounded resources, say a polynomial time algorithm, may perceive the entropy of a random variable to be very different than its actual entropy. Okay, and perceive is in quotes because, as we'll see in the talk, there are different senses in which an algorithm, we may think of an algorithm perceiving the entropy of a random variable. So the most, one of the kind of striking examples of this is the notion of a pseudorandom generator introduced by Blum, Macaulay, and Yao. So a function by definition, so it's a function that stretches some random seed of m bits to n bits that are indistinguishable from being uniformly distributed. Right? UM here is uniform distribution on m bits. All right, so by definition, its output distribution is indistinguishable from the uniform distribution, but the amount of Shannon entropy or even max entropy in the output is at most the seed length m, because G is a deterministic function. So it looks like it has n bits of entropy, but it really only has m bits, or at most m bits of entropy. Okay, just right. And this is the notion of computational indistinguishability. No polynomial time algorithm can tell a random sample of one distribution, in this case the output of the pseudorandom generator on a random seed, from the other random variable, uniformly random n bits. Okay, except with some negligible difference in probabilities. Okay, so Hastad et al. So this is was a qualitative form of pseudoentropy. We didn't really need the definition of Shannon entropy here. You have something indistinguishable from the uniform distribution, but has small support. Hastad et al. Introduced a more quantitative form of pseudoentropy, where they defined a random variable to have, so generalization of this idea of pseudorandomness. A random variable has pseudoentropy at least k if there exists a random variable y, some other random variable that's indistinguishable from x, but y has Shannon entropy at least k. Okay, so pseudorandomness is the special case of this, where the pseudoentropy k is maximum n, the length of the random variable, because the only distribution that has Shannon entropy being its bit length is the uniform distribution. Okay, so yeah.
You bound the length of the variable, because otherwise you can hide as much entropy as you want from the tiny patch of y. It's Shannon entropy.
Can you say one more time?
So
Yeah, it's bounded to be polynomial in the length.
so y has to be a bounded length.
Oh, yeah. Okay, so yes. All right, so, well, I mean, to make sense of even these notions of computational indistinguishability, everything here is implicitly parameterized by some length parameter or security parameter. Okay, and all things are, so there'll be some n hiding, and everything is of length polynomially related to n. And
That somehow makes Shannon entropy behave not too crazily compared to mean entropy.
well, okay, so what we're going to be doing here is comparing, it will behave very differently from min entropy, but we'll be comparing the pseudoentropy k, to the actual Shannon entropy. And as long as we have a gap there, that'll be enough to work with. Okay. But the fact that Shannon entropy can do weird things, like you can get a lot of Shannon entropy from some small probability being random and the rest of the time not having much randomness, we'll need to deal with that. And we'll deal with that by taking many independent samples of random variables. So things concentrate around the average. Thanks. Okay, so a remark about this definition. All right, so we're interested in this when k is larger than the entropy of x, so that the pseudoentropy is larger than the actual entropy. And one remark is that this definition turns out only to be interesting and useful as a lower bound on pseudoentropy. And that's why I've defined it as saying x has pseudoentropy at least k. That somehow you don't get a very meaningful definition if you try to make a similar definition for saying a random variable has small computational entropy. That we say it doesn't make sense as a definition to say x has pseudoentropy at most k if it's indistinguishable from something that has Shannon entropy at most k. It turns out that under that definition, every random variable has is indistinguishable from something of low entropy. Okay, so this is useful as a lower bound on computational entropy. Okay, and so now, so this is a nice definition. What is it good for? Well, Hastad used it as a key component in their seminal result that you can construct pseudo-random generators from any one-way function. Okay? And the intuition for the proof is, all right, so from a one-way function, what Hastad et al. showed how to do from any one-way function is build a random variable, one which you can generate samples from in polynomial time, in probabilistic polynomial time, where there's a small gap between its pseudoentropy and its Shannon entropy. But there is some gap, so its pseudoentropy is noticeably larger, say by 1 over a polynomial number of bits from its Shannon entropy. And then by taking repetition, so this is an answer to Mark's question in part, they construct from x, so this is a new x that consists of many independent samples of the previous one, where we get not a gap between pseudo-Shannon entropy and Shannon entropy, but we get these worst-case notions of entropy. So x is indistinguishable from having high min entropy, okay? And you get something that has small support or is statistically close to having small support. All right? It lies in small support with small set with high probability. And the gap between entropies goes from a small gap, 1 over a polynomial, to a large gap, so polynomially many bits of gap. Okay? And then by some hashing, you can construct a pseudorandom generator. You can use hashing to extract the pseudo-min entropy into pseudo-randomness. Right? Like a randomness extractor, you convert high min entropy into being indistinguishable from uniform, and you can convert the fact that the random variable has small support to it constructing something that has a short seed length. Okay, so this is just the intuition behind their proof. The actual structure of their proof is substantially more complicated than this due to some technical issues that arise in the construction that I'll hint at later. Now we do really have a proof that has this structure, and that's part of what I'll be talking about. But this is definitely the kind of the idea underlying the proof. Okay, so I want to give some intuition on this first step here. How can we get pseudoentropy, a gap in pseudoentropy and Shannon entropy from a one-way function? Okay, so for intuition, let's focus for now on the case that a function is one-to-one. Okay? And consider an input to the function chosen uniformly at random. Okay. So then, if we look at the entropy of x given f of x, that's 0. Because f is 1-to-1, so x is determined by f of x. Okay? On the other hand, one-wayness tells us that given f of x, it's hard to predict x. No polynomial time algorithm can do it except with negligible probability. So this intuitively seems to be saying that x looks like it has some randomness given f of x. Right? It's unpredictable given f of x. So this should be some kind of computational form of entropy, and we want to relate it to pseudoentropy in some way to carry out the Hastad et al. Construction. So to understand what kind of computational entropy we might look for, let's look at kind of the information theoretic analog of this property. Okay, so instead of saying for every polynomial time algorithm, let's take away the polynomial time constraint. And suppose we have two jointly distributed random variables, x and y, such that for every function a, the probability that a of y is x is at most some value p. Okay? Then this can actually and has been considered as a kind of measure of the entropy in y given x. It was called average min entropy by Dodis, Ostrovsky, Raisin, and Smith. And it's kind of a natural conditional version of min entropy here of x given y. All right, if we didn't have y here, and we say for every algorithm A, the probability A predicts X the most P, that's exactly the same as saying that A has min entropy log of 1 over P. Okay? And this is a conditional version of it. So this is saying X has average min entropy at least log 1 over P given Y. Okay. And this turns out to be stronger, just like with standard min entropy and Shannon min entropy in the conditional form. This is also stronger than the conditional Shannon entropy. So this implies that the Shannon entropy of X given Y is at least log of 1 over P. Okay, so now let's look for analogs here on the computational side. All right, so similarly, Xiao, Liu, and Raisin defined this as gave a name to this as a computational analog of entropy. They said that this we'll call this X having to we'll say X has, if X can't be predicted from something else except with some probability P, we'll say X has unpredictability entropy at least log of 1 over P given f of X. Okay, and so log of negligible is something super logarithmic in it. And now what we might hope is that this implies, just like over there, that we have pseudoentropy in the sense that I defined before, that X is indistinguishable from having a super logarithmic number of bits of entropy given f of X. Right? So it's indistinguishable from some other random variable that has this much entropy given f of X.
Computational version of the chain rule apply? Entropy of X, Y is entropy of X plus entropy of Y.
For min entropy holds if you lose something, you have to.
They can be security for now?
All right, so in one direction, I think in one direction it holds, but I don't think in
This is the direction that you want.
no, actually it's not. It's not. All right, so think of a pseudorandom generator.
I mean, you can take X and f of X, where f of X is the one.
The direction.
Right. Yeah, so think of like G, M, UM. This has a lot of entropy, but now you reveal this, and all of a sudden the thing as a whole has low entropy. Okay. All right, so all right, so the question is whether this holds, and, oops, I'm holding it upside down. Unfortunately, it's false, okay? And the problem is that given f of X, X is, you can recognize X completely because the one-way function is easy to compute. So given f of X, given any string z, other string z, you can tell whether it is the preimage of f of X or not efficiently. Okay? And so you can distinguish X f of X from every random variable, from any pair z f of X, any random variable z, where z has noticeable, I mean non-zero or 1 over poly entropy given f of X. Okay, so our challenges, so we can't directly deduce from the one-wayness of f that X has pseudoentropy given f of X. But maybe there's some other way we can convert this unpredictability of X given f of X here into pseudoentropy as we defined it before. And second is further challenge comes in dealing with the case that the function is not one-to-one. And in that case, this condition, as I've written it here, the unpredictability of X given f of X, can hold for trivial reasons, just from the fact that given f of X, there are many choices for X. Okay, if the function is not one-to-one and many points collide at the same f of X, then you won't be able to predict the original value X with even exponentially small probability, but it's not for computational reasons. It's just for information theoretic reasons. Right. No, the original thing doesn't either because it's just not true that x has pseudoentropy given f of x. That's what that example says. Okay. All right, so this box I should have just crossed out, not just the arrow. Yeah.
You can still hope that like half of the bits of x, you know, if you're just given half the bits of x, that it still has pseudoentropy.
Yes, that's a good. So that's a good intuition, and we'll show something like that.
Okay.
Yeah. Thanks. Okay, so what did Hastad et al. Do to deal with these problems? They looked at the following construction. They take f of x, and then they don't take x as it is, but they hash x and hash out a random number of bits from x. So you pick j at random from 1 to n, and you choose a random hash function from a certain kind of family. You need more properties than it just being a universal hash function. And you output j bits of h of x. Right? And the intuition is, and what they show is that this random variable has more pseudoentropy than its Shannon entropy. Okay, by a small amount, like not with a log n gap, super logarithmic gap, but that divided by n. All right, and this is what we were maybe hoping for from the intuition before. Yeah, sorry, terrible. All right, so notation. So this is h, thank you, is entropy. And this h is a hash function that is written in capital letters because it's a random variable. Yes, thanks, Steph. Okay, and the intuition is this choice of j is kind of guessing the number of preimages of f of x. So, it's supposed to be a guess for the log of the number of preimages, so how much entropy there is in x given f of x. And so if we guess that value correctly, then the first few bits of this will be statistically close to uniform just by leftover hash lemma. We're hashing out the kind of the information theoretic randomness in x. And then we can take j to actually be log n bits larger and hope that by the sort of Goldreich-Levin theorem that you get log n pseudorandom bits by hashing x from the computational hardness in finding any preimage of f of x. Okay? And you lose this 1 over n here because of this kind of guessing how many preimages there are, the guess of j. There's only one value or a small number of log n over n values where you get a gap, where you get the computational entropy. All right, so the new thing we can show, this was conjectured in this earlier paper with Heitner and Reingold, and now proven in this new work with Colin Zheng, is we consider f of x together with x, the bits of x, but instead of reasoning about the pseudoentropy of that, we introduce a new notion which we call next bit pseudoentropy, and we can show that this has next bit pseudoentropy n, which is exactly how much entropy there is actual entropy there is in f of x and x, because x is n random bits, and f of x is determined by it, plus the log n super logarithmic number of extra bits that come from the computational hardness of inverting f. Okay? So I'll define in the next slide what is next bit pseudoentropy, but assuming there's a reasonable definition for that, the advantages of this construction are there's no hashing. Okay? So in the Hastad et al. Result, you needed both kind of universal hashing properties as well as this kind of Goldreich-Levin local list decoding kind of property for those who know about that. Right. So now, oh yes, and also we don't have a collision of notation anymore. A second advantage is here we really know how much actual entropy there is. There's just n bits of actual entropy, and that's what we want to compare to. In the Hastad et al. Construction, and this is actually a source of many of the complications of their construction, is they can show that the pseudoentropy in W is larger than its Shannon entropy, but we don't know what the Shannon entropy of W is. Okay, that may not be easy to compute. And so they go through extra complications where you have to try all possibilities for the Shannon entropy of W, build a pseudorandom generator in each case, and try and combine the pseudorandom generators they get out, knowing that one of them will work properly. So that goes away. And the second is we get all the pseudoentropy, extra pseudoentropy that we expected from the intuition, from the hardness of inverting F.
So if F is a one-way permutation, does the Hill notion match here? Can you use
No, so it's even an advantage in, does the notion match? No, so it's a different notion. This is a weaker notion, okay? Next bit pseudoentropy is a weaker notion than pseudoentropy. What? Even for a one-way permutation, okay? The pseudoentropy is not any larger than n, right? This is the example we saw before, f of x and x. The pseudoentropy is just n. So it's a weaker notion, but you do get something new in that case as well, because even in that case, one had to do some hashing in Goldrake-Levin to get a gap here. OK, good. So that's right. So as David just pointed out, all right, we do need to change the notion of pseudoentropy, because as we mentioned before, f of x and x together, you can tell apart from everything of entropy larger than n, because everything is determined by x in an efficiently computable way. All right, so what is a next bit pseudoentropy? So this is along the lines of what Ankur was suggesting earlier. So what we do is we imagine, don't read all this notation yet. Let me say it first at an intuitive level. We imagine the adversary is not given f of an x and x all at once, right? But it gets to read this sequence from left to right. Right, so first it's given f of x, and we ask, how much entropy does it look like x1 has given f of x? Okay. Then we give the adversary f of x and x1. We give it x1, and we say, how much entropy right now does x2 look like it has given f of x and x1? And so on. And we do this, add this up over the n bits, and that's what we call the next bit pseudoentropy. Okay. Formally, we ask that there exists a sequence of random variables y1 to yn that are jointly distributed with x and f of x, okay, such that for every I, xi is indistinguishable from yi given the prefix of f of x and x1 up to xi minus 1. And secondly, if we add up the entropies, all right, add up the entropy, well, first of f of x, so that part we're not changing at all. We're not looking for anything extra there. So we have the entropy of f of x plus the entropy of all the yi's given the prefixes. We get n plus something super logarithmic in n. Okay, and this is like a quantitative generalization of the notion of next bit pseudo-randomness that was introduced by Blum and Macaulay, okay, and shown to be equivalent to standard pseudo-randomness by Yao. Here, this is similarly where think of this as a next bit analog of pseudoentropy, where you get the bits one at a time. But in this case, we're exploiting the fact that it's not equivalent to standard pseudoentropy. So that kind of the chain rule doesn't apply for this notion. That the next bit pseudoentropy is larger than the actual pseudoentropy, which is only n. Right, any questions? OK, so what are the consequences of this? So a simpler and more efficient construction of pseudorandom generators from one-way functions. So in particular, one quantitative improvement, so the results of Hastad et al. And all right, so this was a construction sketched in Hastad et al. and formally proven by Hollenstein. If you start with a one-way function on n input bits, you get a pseudorandom generator whose seed length is something like n to the 8th. Okay? And and with this new notion.
Sketched in Hastad at all?
So the proof, the thing that they fully prove in Hastad et al. Is n to the 12 or something like that. And then they have a section sketching how to get a better, save a bit in the construction. But I don't think they invested a lot in trying to optimize every n there. But using the ideas there, it seems like n to the 7 maybe is what one can get because of the sort of technical difficulties of guessing the entropies and all of that seem to lead to something like n to the 7. So now we can get a construction with seed length n cubed or O tilde of n cubed. Maybe it's n cubed times log n. So in the paper with Haytner and Reingold, we had n to the 4th, and that's also something in this new paper with Colin, we get it down to n cubed. So it's not still not practical, but it's the construction is significantly simpler than the previous ones. If there's time, I may show even just what the final construction looks like, and at least getting towards a construction that one might want to use in practice is now one can at least dream about it. You shave off 2 more factors of n, and is what we need to do, and who knows whether that'll be that's possible. It's an open problem.
I mean, in practice, you would just use the one permutation.
That's a good question. You're right that many of the sort of ad hoc functions that people write down do give rise to permutations, but not all of them, right? So the kinds of what? From the more sort of number theoretic. So what I'm imagining here is that those things people want to use as little as possible in practice. Anything number theoretic, right? They want to use things like AES or MD5.
But those are permutations.
So the stuff that they use for hash functions doesn't directly give a permutation, right? Those are hash functions, so they're
For hash
right.
functions,
But it's a good point. Exactly where, in what context you'd want to use these constructions. So the overall aim would be to have something that you make much weaker assumptions on the building blocks than they currently do. Right now, they assume all kinds of magical properties from these hash functions that they have not turned out to succeed in actually providing. Right? Collisions have been found in MD5. But anyway, that's not so much the motivation. I mean, they're definitely trying to get something simpler and that we really understand what's going on is the main motivation here. If we could get something that was within reach of practice, then we turn to the question of exactly where in practice would you try to use something like this. Okay, so let me give for this new result with Colin about showing the next bit pseudoentropy of f of x together with the bits of x. The key component is this new characterization of pseudoentropy, of pseudo-Shannon entropy, or conditional pseudoentropy. Right? So I have 2 jointly distributed random variables, y and z. Think of y as kind of long n bits. Right? So algorithms are running in time poly n here. But z is short. Okay? Z is like, think of it could be 1 bit or logarithmically many bits. Okay? And we're interested in characterizing the pseudoentropy of z given y. Okay? So I want to know, does there exist a z prime such that z is indistinguishable from z prime given y, of noticeably larger entropy than z has given y. Okay, so I'm comparing the pseudoentropy to the actual Shannon entropy of z given y. I want that to be bigger by some delta amount. Or delta need not be between 0 and 1. It can be larger. It can be up to log n.
So this is you're forgetting next bit. Next bit pseudoentropy. You're back to pseudo.
Right. So I'm back to pseudoentropy, but conditional pseudoentropy. And actually, why don't I? It's a good point. So the point is that what we're doing here is we're just summing up the conditional pseudoentropies of the bits. And so if we really understand conditional pseudoentropy, we should be able to analyze the next bit pseudoentropy by just analyzing the conditional pseudoentropy of the successive bits, which is in fact what we do. Okay, and we give an exact characterization of this in terms of how hard it is to predict z from y, but in a particular sense. Okay, so so z is a random variable given y. So I consider, what happens when you have a probabilistic polynomial time algorithm A, and we give it y, and it's trying to predict z, or more accurately, what it's trying to do is sample the right distribution of z given y. Okay? So if z was just a function of y, right? That's maybe a good case to keep in mind. Then A is somehow trying to predict, figure out this right value, and put as much probability mass on the correct value as possible. But in general, if z is, say z was just a random bit given y, then the best thing for A to do is just toss a coin and output a random bit.
Just like in distribution of one-way functions.
Yes, yes. That's right. That's
so
right.
The bound on the length of z comes just from, you need it's related to the polynomial time.
Yes.
Right? And there is some enumeration of the value, possible enumeration.
Exactly. Exactly.
So you could define it for larger z, but you would win.
Well, this equivalence would be false. And in fact, the example we had before of f of x and x would be a counterexample. Yeah. And all right, so the characterization is the gap between the pseudoentropy and the Shannon entropy is exactly the minimum distance that an efficient algorithm can attain between the distributions y z and y a of y. All right? And distance is actually just KL divergence, minimum KL divergence between these two.
Is this distance metric very important?
It is for this equivalence. What?
Z is 1 bit, then it should not matter. Oh, because it's y.
Well, that you still will take expectation over y, but and then it matters, what you're taking expectation over. So, yeah.
So there is no analog of such a theorem for entropy as opposed to conditional entropy?
There is. So we do have an analogous version of this. We can avoid. So the reason you wouldn't have one is because of this, the random variable that you're really interested in, which is z.
You can allow your algorithm to run in exponential time in the length of that value, but given that.
I'm not sure. I'm not sure whether, so in the non-uniform case, things would get trivialized if you let it run in time exponential in the size of the domain, because everything can be hardwired. Okay.
So you need, but still you could have, you could let y be fixed, length and fixed, so all zeros fixed.
All right, so I'll tell you what we know, and then, there definitely there's a gap. I don't know that everything we don't know is impossible to show. So what we do know, if we have both a uniform and non-uniform analog of this result. For the non-uniform analog, we do have a version of it where we don't have this constraint here, okay? But we changed the task of A here. A is no longer trying to sample the right distribution, but instead compute a measure that, when normalized, gives something at small divergence. Okay, so given a value y and given a possible value here, it gives you some measure to put on that point. And then if you normalize it to a distribution and compute the KL divergence, you get in kind of that'll give you an equivalence.
But that was not my question. My question was not about uniform versus non-uniform, but about the.
Oh, but in that.
That's not conditional.
Right. So that one, because we remove the length constraint here, it's interesting even if you remove the conditional. Okay. Yeah. And gives you it gives you a characterization of pseudoentropy and the kind of unconditional pseudoentropy.
So if you replace pseudoentropy with entropy and polynomial time with any time, then it's also reversed.
Yes. Yes. Oh yeah. So sorry. This doesn't. Right. This vacuously can't hold. Right. I mean, the entropy can't be bigger than the entropy.
That's bigger than delta.
Delta will be 0.
Delta will have to be 0.
If the entropy of z given y is bigger than delta, then there's no.
Here I have the. I need for this to say anything. I need a gap, a non-zero gap between the pseudoentropy and the actual entropy.
Conditional entropy is the maximum or the minimum of this quantity overall case. Overall terms. That's what the
It's just bigger than delta.
I'm not sure. It doesn't fall. I mean, you can remove the time constraint on everything, and the theorem is still true. But I don't know that it implies what you're saying. Yep. Okay, so all right, I mentioned that this special case. I said this is where z is a function of y. Then it's really capturing hardness of prediction. But we want to handle the case not just where z is determined by y, for the same reason that we want to handle. It comes from the fact that we want to handle functions that are not one-to-one. So the bits of x are not determined given f of x, and we want to get pseudoentropy, understand when its pseudoentropy is larger than the actual entropy.
I must be wrong, but somehow it feels that expression hz given y is missing from the right-hand side of the divergence. Like if you think about, let's say, no, I'm not missing something, right? Because if you think of, like, let's say, z is completely independent of y as a example.
A would just be output in a random distribution
Exactly.
of z, and then this divergence would be 0.
Yeah.
Oh, I see. Right. Okay. Thanks.
Okay, and okay, and this is this other point that this theorem would be false if we didn't put the length constraint. This is what came up in Avi's this O of log n bits here. We need a small alphabet for z. Otherwise, this f of x, so taking y to be f of x and z to be x would be a counterexample. We said it has no additional pseudoentropy, but it is hard to predict x from f of x, and it can be shown to be hard in this sense here with KL divergence also. That's, yeah, and that's the gain from looking at things bit by bit. Okay, second remark is that it may not be immediately obvious, but this is an analog of the Impagliazzo hardcore theorem for Shannon entropy rather than min entropy. Okay, so there is a way of interpreting the Impagliazzo hardcore theorem as giving a characterization of pseudo min entropy. Okay, that's the same thing that we called unpredictability. No, pseudo min entropy, indistinguishable from high min entropy here. Over here, and putting standard hardness of prediction, where we don't look at the divergence, but we just look at the probability that a of y equals z. Okay, and that the Impagliazzo hardcore theorem is exactly that statement for the case also where z is 1 bit long, but now we can show it for log n bits also. And if you don't know, don't worry about it if you don't know the hardcore theorem, or it may not be, it takes some translating to get from that formulation to this one.
So z somehow figures into the blowups in this reduction.
Yes. Yes. Okay, so now maybe let's see how it implies next bit pseudoentropy from a one-way function. So we have a one-way function. What? You would rather me give the proof of the characterization? I don't think we'll have time, nor do I have slides on that, but that's something offline. Of the characterization? Let's see. I could skip the rest of the talk and then just try to say a bit about the... All right, so maybe I've given enough intuition for... So Avi, are you suggesting that's what I do?
Yeah, it's cool and it's different than what standard proofs like this that people can guess. But we can ask everybody, and we can give you more time anyway. So.
Okay, all right, well, why don't we do a poll? So who would like to see the...
Can you fast forward through the existing slides instead of...
No,
Is it a lot of slides left?
The talk as planned would fill up the rest of the time. But I can just switch now and talk about the ideas and the proof of the characterization. And since I haven't prepared as a talk, I'll probably not miss some details, but I can give the main ideas. So who wants to see the proof of the characterization? And who wants to see the rest of the slides? Okay, it seems more people are. All right, since the slides. All right, so I've given this talk in a number of other places, videos and slides online. I guess so people can see the slides if they're interested in the rest. I just mentioned there's one thing that I am not talking about today is that there's an interesting kind of seeming duality between the kind of notion of pseudoentropy that this next bit pseudoentropy that we're using here and a notion of pseudoentropy that arises on the right side of this picture that we don't fully understand yet, the duality, but many of the results have come by kind of mutual inspiration, and the results look superficially very similar, and we're trying very much to understand this duality. And the notion that arises over here is useful for kind of upper bounds on notions of computational entropy, ways of saying that in some computational sense the entropy of a random variable looks less than its actual entropy. Okay, so
one thing from this rest of the talk of how to use the characterization in the construction is why is it important to have a characterization in which the KL divergence features.
Right.
So that's the one thing you can say about using
it's not important that it was KL divergence, but it works out well for us. I mean, what we cared about was characterizing the pseudoentropy. And the reason we want to characterize the pseudoentropy is because that seems to be all we can get directly from a one-way function because of not knowing how the entropy itself in X is a random variable. And then when you want to take many copies to turn it to min entropy, kind of Shannon entropy is the right measure for saying what will happen when you take many copies. So here's where the KL divergence. So it's just what I said. So given f of x, you can show one-wayness implies that it's hard to produce something at divergence O of log n from x. Okay? It's kind of like saying this is a type of sort of distributional one-way function type property that follows from the standard one-wayness. And then when you break things into bits, you lose a factor of n in the divergence so that you have O of log n divided by n bits of hardness of predicting in per bit on average. And then you apply the characterization to the individual bits, and then add things back up again. You get your log n gap.
Is there an interpretation of these steps through like boosting in any way? I mean, is there an analogy?
Boosting seems to come up more in the proof of the characterization.
Okay.
the uniform proof of the characterization.
Okay.
Yeah.
That's basically what happens in the hardcore separation.
Right.
Right.
So, do you use if you replace scale diversion with statistical distance, does it make any difference?
It's a great question. I don't know.
Take
We
delta to delta square. Is your proof sensitive to such difference?
But it will not probably not give exactly the same power.
I don't know if you put statistical distance here and ask what does it characterize? What form of pseudoentropy does it characterize? Is there one that it characterizes exactly? I don't know.
You lose a square factor.
Yeah, but whether there should be something that it characterizes exactly, and I don't know what it is. No?
No, because there is some weirdness. It's like, yeah, it's depending on the regime, it can vary from delta to delta square. Yeah.
No, I know it's not going to characterize Shannon entropy, but maybe there's some other entropy notion or something that it characterizes.
But is your proof sensitive? So which
Yeah,
which direction are you using? You're using
But
I'm
also,
using-
you can only-
but I'm using this direction. Because the one-wayness gives you hardness of predicting, and then I want to deduce pseudoentropy.
but it also gives you hardness to predict with delta square for the range of parameters you're using. It's always
No, we can't afford, all right, that's a good, actually, we can't afford to lose a square or even a constant factor in delta here. It's important that we don't lose. There's a negligible additive thing that I haven't written here, but it's really important it's delta and delta, not delta squared or 2 delta. The reason is that, it's, maybe we can afford it in the delta. I don't want to lose in this.
No, that's
This
fine.
part, I don't want to lose.
but
Yeah,
in delta
you're right.
You just get your 1/4 of the
Yeah, so,
that's fine.
well, you'll pay in the seed length of your pseudorandom generator by a
Descent,
larger ends.
you
Yeah,
will not get in cube, but you'll get still.
yeah, seems like it.
It's striking that this is the same delta that gives
No, of
if you
course.
plug the, yeah,
Okay, so anyone know how to raise the